this session, we'll be getting into working with scenarios with OpenQuake. So we'll be going through what you can model in terms of scenario, hazard and risk assessment with OpenQuake. So I'll just give you a brief overview of what OpenQuake is capable of. It's a small presentation, and then we'll switch after that to working with one of the three ruptures that Keegan has selected. So we'll be working, we'll have a hands-on session with the Charleroi event. So once that's done, once everybody's got a hang of how the software works and what goes where, the idea is that the next part of the session will be all of you working on the other two scenarios. We prepared a short series of assignments for you to work on in the second half of the session. So to start us in the morning, how GEM usually works is through these different modules that integrate into the picture of seismic risk in a region, starting from the seismic hazard, the exposure, the physical vulnerability, moving into seismic risk, and then integrating that with some socioeconomic information as well to come up with the picture of integrated seismic risk. So today we'll be looking at scenarios using the same approach. So the hazard part would comprise information about the rupture, geometry, the magnitude, the location of the event. The exposure part, Murray covered in the morning. So we provided you with the exposure models for Ontario and Quebec, the two provinces of central Canada. We split them up into several files so that you can mix and match the census divisions that you might be interested in working with. So because if you work with the entire provinces, it can be a bit too unwieldy. And then the third component is the physical fragility and vulnerability functions. When you come in, what kinds of earthquake ruptures can there be? What are the different types of earthquakes? Or different types of earthquake fault geometries that you can model in OpenQuake. So a lot of you are, we saw in the morning that your background is seismology or you're a geoscientist, so you're pretty familiar with all of this. For others, it's a basic primer on the different kinds of faulting mechanisms that lead to different types of earthquakes. You can have normal faults, you can have strike-slip faults, or strike-slip fault is where the two plates are moving in lateral. There's lateral movement between the two plates, they're sliding against each other. There's frictional forces that lead to earthquakes. There can be vertical slip as well, which will be classified as normal or reverse faulting, depending on whether the stress between the plates is tensional or compressional. So if the plates are moving away from each other, and the hanging wall block is the one on the top of the fault. If it's moving downwards compared to the footfall block, this would be called normal fault. Otherwise, the opposite case would be a place where you have the two plates compressing. You'll have a reverse fault. The thrust fault is a kind of reverse fault with a very low tip angle. These lead to different kinds of earthquakes. So you can model all of these different geometries in an OpenQuake rupture scenario. So some of the terms that you'll hear, you'll have to use a lot when you're modeling rupture geometries are the three angles, which are called the strike, the dip, and the rake. So you'll see some of that in the exercises today. So basic definitions are if you have the two plates, look at the fault trace, which is the projection of the fault on the surface of the Earth. If you look at the angle that makes with this line makes with the north, that's the strike angle of your fault. The dip is the angle made by the fault plane with the horizontal surface of the Earth, and the slip angle is the angle of a slip between the two plates compared with the horizontal. Some other information that you need when you're modeling earthquake ruptures is the type of fault, the magnitude of the event, the geometry of the rupture. So this could include definitions of the rupture plane itself, or some other ways of defining the rupture geometry that we'll get into. In terms of the hazard outputs for scenario types of analysis, one of the key outputs from this kind of analysis would be maps or fields of ground shaking intensity. So you could be looking at trying to predict maps of peak ground acceleration, or it could be also for other intensity measures such as peak ground velocity or spectral acceleration at different periods. So these would be a critical output in the scenario hazard analysis. So OpenQuake can allow you to model the rupture and then produce ground motion fields from those ruptures. So we get a bit into this as well. To go from a rupture geometry and magnitude of the event to these ground motion fields, a key step in between is the link is made through the ground motion prediction equations, which Michael touched on in his presentation earlier this morning. So ground motion prediction equation, for those who are not familiar with this term, is sometimes called GMPs in short, sometimes also called GSIMs, which are ground shaking intensity models. What these do is they try and take in some input variables related to the rupture itself and also related to the sites that you're looking at predicting the ground shaking at. So if you have the rupture and a few sites surrounding the rupture, sites would be locations of interest. Then based on the magnitude of the event and maybe some measures of distance between the rupture and your sites, that could be some other additional parameters. We're trying to predict the intensity of ground shaking at these different locations around your rupture. So these ground motion prediction equations are usually, most of them are regression equations based on previously observed ground shaking in similar regions. So there are several of these GMPs which have been derived for various tectonic regions around the world. Many of them have been implemented in OpenQuake. Here we see a simple form of these equations. This is a GMP for induced seismicity in North America, developed by Gail Atkinson. So it has a very simple form. So the log of y is the ground shaking intensity here, is predicted as a function of the magnitude, a function plus a function of the distance from the earthquake rupture to the locations. So in this case, it's a very simple form. So in most of these ground motion prediction equations also give you a measure of the uncertainty in this prediction. So you'll get a measure of the mean or median ground shaking, and also some measure of the uncertainty in ground shaking. You can see that these equations can get quite more complicated as well, depending on the area of interest. So in addition to the magnitude and distance, these prediction equations also may include input variables such as the style of faulting, the hanging wall geometry, shallow site response variables. If you're trying to model the basin response, there could be other parameters that go into these GMPs, measure of the hypocentral depth, fault dip angles, and other kinds of input variables. So if you are interested in seeing which ground motion predictions are already available in OpenQuake, you can go to docs.openquake.org and you'll find a link to extensive documentation of which ground motion prediction equations have already been implemented into the OpenQuake hazard library. So as part of the implementation of the 2015 hazard model for Canada, all of the Canadian GMPs have also been incorporated into OpenQuake, and we'll be using some of them in our exercises today.
Just worth mentioning that in the exercises today, the ground motion models of the 2015 model, the only parameters that are used are the magnitude and the distance. So just Many GMFs have many parameters, but in the National Building Code 2015 model, it's a function of magnitude, distance, and area.
So many of these GMPs use different measures of distance from the fault rupture to the site. Some of these distances could be the R rupt. It's the closest distance measured from the rupture surface to the site. The first one, RJV, is what's called the Joyner-Boer distance. It measures the closest horizontal distance from the site to the vertical projection of the rupture. So if you have a rupture, which is, if you project that fault surface to the surface of the Earth, then you're measuring the closest horizontal distance from that projection to your site in this case. So different GMPs use different measures of distance, and that can have an effect on the patterns of ground shaking that you see when you plot the outputs from these ground prediction equations. Some others use just a hypocentral distance, so it's just measuring the distance from the hypocenter of the earthquake rupture to the different sites. And because OpenQuake has a large library of GMPs implemented, you can quickly switch between different GMPs that could be applicable to the tectonic region of the study area and see the effect these have on the ground shaking, and similarly how this translates into estimates of damage and loss. So, so this example, I'm just going to show a few sides of the different kinds of simulations of the scenario that we'll go through today for the Charlevoix scenario. So in this case, we're looking at the 2014 West Napa earthquake, which is a magnitude 6 earthquake that happened in the West Napa Fault. So once we model the rupture geometry, we can look at the effect of the choice of the GMPs on the ground shaking. So here the first map is showing the ground motion prediction equations, the median ground shaking intensities as predicted by the Abrahamson et al. 2014 GMP. And this is showing the median from the Boer et al. 2014 GMP. Both of these use the RJB distance as a measure of the distance between the rupture and the sites. And this is something that would not be applicable to this region, but just to show the difference in the kinds of patterns that you see in the ground shaking if you switch to GMPs that use the hypocentral distance. This is the map for the median ground shaking predicted by the Acker et al. GMP for. So apart from median ground shaking, OpenQuake also has the capability to run through Monte Carlo simulations of the ground shaking. So you're not just looking at the median ground shaking, but you're now sampling from the full distribution of predicted ground shaking given the magnitude and distance. So again, with the same GMP, now you could be producing multiple ground motion fields. And this is the way to propagate the uncertainty that is inherent in these models all the way through to damage and loss estimates. So here, like if you're running, let's say, a few different simulations of the same event, so this is a Monte Carlo simulation of the ground shaking using the Abrahamson et al. GMP. So this is the first simulation. This is the second one. This is the third one. So you can see already that there can be quite a bit of uncertainty in the predicted ground shaking. So after we finish with the seismic scenario hazard calculations for the Charlevoix scenario, we'll do a bit of work on the damage and loss estimates for the same scenario as well. So for that, we have the exposure, as Maria already mentioned, and then we have also, we provided you with fragility and vulnerability functions that we will be using for the scenario. So basic definitions of these concepts. These are not always used in the same way in the literature and in other places, but in our work in GEM, what we mean by fragility functions is you're looking at a prediction of the expected level of damage, which is usually described through a set of discrete damage states. So you're looking at predicting the probability of exceeding one of these damage states as a function of ground shaking intensity. So you would select an appropriate measure of intensity for different structural types based on their structural characteristics. So it could be spectral acceleration at different periods that forms the intensity measure selected for different structural types. And on the y-axis, on the plot on the left, you will have a set of curves that are predicting the probability of exceeding a set of given damage states as a function of that intensity measure. And by vulnerability functions, instead we mean trying to predict economic loss or human loss as a function, again, of a selected intensity of ground shaking. So in this case, we would be looking at distributions of economic loss or human loss as a function of shaking intensity. So there are a few different ways in which fragility and vulnerability models can be input into OpenQuake. You can model fragility functions either using continuous cumulative log-normal distribution functions, which would be smooth functions that you fit on regression, using regression analysis on empirical damage data or on simulations of damage through analytical modeling of your building behavior in different earthquakes. Or you can model fragility functions as discrete functions. So these would be just a set of points that give the x and y coordinates of these different damage states. So this is just a representative picture of how these functions look like. So these are, again, derived from simulations, analytical simulations of, in this case, all four of these plots are showing functions for what's called the W1 structural type. This is low frame residential wood housing. So now the four plots are showing differences in the level of ductility, the level of seismic ductility, because these represent the same structure but designed according to different levels of seismic ductility requirements from different seismic design codes. So you can see that the pre-code fragility functions predict higher, much higher damage for the same ground shaking compared to the high code functions, which seem to be very difficult to collapse. And then you can also have something called consequence models. This is not something that we look at in our exercises today, but if you're, these are ways to link estimates of damage from a scenario or from probabilistic analysis to different kinds of consequences. So if you know that your structure has reached a certain level of damage, then that level of damage would be linked to different kinds of consequences. So these could be the direct economic consequences in terms of how much would it cost to bring the structure back to its original state before the earthquake. So this would be direct economic loss, but it could also be linked to different levels of injuries that you can expect occupants in those buildings to suffer, or it could be linked with business interruption, the amount of debris generated. So these would be different kinds of consequence models that you can link with the damage outputs from scenarios. So this is something that Murray has been working a lot. Maybe he'll talk a bit about more of this tomorrow. There are also quite a few different ways in which you can input vulnerability functions into OpenQuake. So you can either model them using continuous distributions. Again, this is a way to make sure that you're propagating the uncertainty that is inherent in these models all the way to your damage or loss estimates. So you can model the vulnerability functions as log normal distributions. So given a level of shaking, you could model the expected loss ratio as log normal distribution or as a beta distribution, or otherwise, if you have some empirical data which relates ground shaking to the level of economic loss observed, then you can also fit direct discrete distributions of the loss ratio conditional on the ground shaking using probability mass functions. So you can input different kinds of vulnerability functions into OpenQuake. So that's just a very quick primer on the components that go into an earthquake scenario exercise. So we'll be starting with one of the three scenarios that Tegan introduced just earlier. So we'll be starting with the Charlevoix magnitude 7 event. This is something that occurred in 1663. So this would be, I guess, an exercise trying to look at what would happen given the current exposure, given the current state of the buildings in that region. So before we move into the hands-on session, I'll stop here for a bit and ask if you have any questions just on these aspects of scenario modeling.
Sorry, I have a question. If it was too easy, I apologize. So in Fragility's function, the x-axis is your red motion level, the y-axis is probability damage
of damage, so it's different. So you can model damage using this discrete damage states. So for each kind of structure, you could define what exactly you mean by slight damage or moderate damage, extensive damage, or complete damage. So these would be some measures of damage, and then on the y-axis of those functions, you're looking at the probability of exceeding each of these increasing levels of damage given the ground shaking.
So it depends on type of structure.
Yeah, it depends on type of structure. So for masonry structures, slight damage could be the first moment when you start seeing cracks appear in your plaster, or start seeing the falling of the cover concrete in reinforced concrete structures.
Like homes, for example, is it what is damage?
These are not defined usually by building codes, but there are other guidelines which help you define these damage states. So usually these would be also very closely linked to the amount of money you would have to spend to bring them back to the original state. So if it's minor damage or slight damage, it's usually just superficial damage. So you might just need to repaint or replaster your walls and have some broken windows in the place. But if it's extensive damage, that means a structural engineer would be involved. There would be significant repairs, and that may cost you close to maybe 25 to 50% of the entire cost of your structure to bring it back to its original state. Something like complete damage would be either it's collapsed and the structure is destroyed, or it's in let's say a precarious condition structurally. It's not sound enough to occupy again, or any repairs would not be sufficient to make it safe. So then again, it's as good as being destroyed. So then it would have to be demolished and replaced. So these are there are different ways of defining these damage states. For the US and Canada, HAZES has good definitions of damage states for different kinds of structural requirement. US and Canada.
How do you define the sleep on the floor?
How do you define the slip on the floor?
Yeah, in this case, for example, because I see the magnitude,
Yeah.
I see the kinematics, and geometry.
I would ask either Tegan or Michael to.
It's determined by the magnitude, and so if you have some fixed rigidity and the area of you assume that the amount of actual slip will be
Define as not.
yes, yeah.
It's the magnitude, it depends. So it depends on the GMP you use. So some GMPs might not be formulated to moment magnitude. So it's the magnitude that the GMPE wants. Yeah, so In general, I agree it's small in magnitude, but not in all cases.
In theory, could it define a distributed sleep instead of
No.
For not in OpenQuake.
No, not really.
That's not a feature, but if you did that in another program to get or just wrote your own script to calculate the magnitude from that, then you can use GMPS that take a moment magnitude.
No, but in the simulation, because I expect the simulation of the PGA also dependent, the location of PGA being dependent where what the sleep is, what the maximum sleep.
You could, if you can convert it to a shape map using the USGS tools, then you would be able to import a shape map into OpenQuake.
It doesn't have like rupture kinematics and these types of fault styles.
So that's where you consider the requirement without considering the details.
It doesn't consider like rupture dynamics.
More questions? Okay, so what I'm going to do is switch from this presentation to I want to briefly go over the materials folder that you downloaded. I'll give you a brief idea of what you can find where in those folders and how it's structured. And then I'll also introduce you to the QGIS project that we prepared for this workshop. Again, show you what kind of information is available in the different layers. And then we'll switch to modeling the structure in OpenQuake. So I'm using a Mac. So those of you who are following using Windows or Ubuntu, you'll see slightly different versions of the tools and of the folder structure. So in the OpenQuake workshop folder that you downloaded, there are 4 say major directories. There's one on references. It just has the different manuals connected to OpenQuake and also to the 2015 model. There's also a reference about the census hierarchy. That was a question in the morning, so you can take a look at that as well. Like how are the different what is the geographical hierarchy of the different divisions? So you have the province level aggregation, and then you have the census divisions, subdivisions. These are statistical definitions, and then there are administrative divisions as well. So the census information is available at the dissemination area level. So there are 56,590 of these across Canada, and a lot of them are in these 2 provinces that we're working on in these exercises. So if you're interested, you can take a look at that. If you look into the exercises directory, again, we have 3 folders. Today, we'll be looking only at the scenarios. There's also a spreadsheet summary of the exposure model that you'll be working with. This is something that Murray has provided. So because the exposure files are collected in a series of CSV files, so if you want to know what information is represented in the exposure model, this provides a very good overview. So I'll go through that a bit later when we finish with the hazard part of this workshop. And for tomorrow, we'll be looking at the probabilistic seismic hazard analysis and the event-based hazard and risk analysis folders. In the datasets directory, we have several of the datasets that have been compiled as part of the national risk model by Murray and others. So the exposure files are available inside the exposure directory. We've zipped them because Otherwise, they can be quite huge. So you'll see two different zip files for Ontario and Quebec, different provinces. And if you unzip them, they are a series of CSV files for each of the census divisions inside those two provinces. And then we have also created an exposure covering just the Quebec City Windsor corridor, which is the heavily populated area of these two provinces. The files are related to the 2015 hazard model are in the NBCC 2015 PSHA folder. We'll go through them a bit in tomorrow's presentation by Michael, and then we'll have a short session on using those files. In the ruptures directory, there's a set of rupture geometries that Murray has prepared. Most of them are for Western Canada, but you'll also see the files for the 3 scenarios that we'll be working on today. So we will produce one of these files in the exercise, and then you will be able to create these geometry files by yourself as well for other scenarios if you're interested. So these are divided into Eastern Canada and Western Canada. And inside, you'll find OpenQuake input files. So these are rupture geometry definitions in the OpenQuake format. There's a folder which has VS30 information for the Quebec City Windsor corridor. And we'll be using clipped versions of this file for the scenarios that there should be in the scenarios. And then the fragility and vulnerability files are in a folder called vulnerability. So that's the datasets directory. And then the last one is the GIS directory. This has all of the boundaries and other layers of information that go into the QGIS project that we've shared with you that cover the 2 provinces of Ontario and Quebec. So that's it in terms of the data in the folders that you've downloaded. And now I will switch to the QGIS project. So if you double click on the centralcanada.qgis file, it should open up QGIS. And you should see something like this when you first start the project. You should see a view of most of Canada. I'll wait a bit until everyone has loaded the project before I start going through the layers to tell you what is where.
So while everyone is opening, you can continue. In this case, it's just that the data sets folder are the real models that Natural Resources Canada has been preparing. Yeah, will be the ones, at least the part of the exposure that will be similar to the ones that will be released next year. The exercises have a set of simplified parts of the models just because we wanted to run very fast and be able to do some examples. But the idea that you will have that data once you go back, you want to use it for a real case in your work or in your research topic, you can go and start using those files.
Is everyone here on the QGIS project? Still loading. Let me just plug in my laptop while everybody's.
Do you mind showing once again from your file structure how you got into the GIS project?
Okay, so for those of you who missed it, I'll show you again where the GIS project opens from. So inside the workshop materials, you have these 4 parent directories: datasets, exercises, GIS, and references. So if you go into the GIS folder, there's a file called centralcanada.qgz. That's the QGIS project file. If you double click on that, that should open up your QGIS application, and you should see the view I'm seeing here on my screen.